Okay, so we have a guest lecturer today, Mark Scheel, who is a senior postdoctoral scholar in my research group. He's going to tell us about gravitational waves from the mergers of black holes and perhaps from other sources where you have to do the computation of the waves using full-blown numerical relativity. Mark was trained in numerical relativity at Cornell University by Saul Jokulski, and he's one of the world's handful of really great experts on this topic. So,
thank you. So, today I'm going to talk about numerical relativity. Which is essentially the job of solving Einstein's equations using supercomputers. And to start out, I'm going to give a little motivation by talking about some of the sources that we're concerned with. So the first source is something that you've heard a little bit about already. This is binary black hole coalescence. And I guess I can draw a little picture where you have two black holes. For now, we're going to just consider them to be equal mass, but you can do the same thing for unequal mass if you want. And these black holes are in binary orbit and lose energy due to gravitational radiation and eventually collide and merge. So for LIGO 1, it turns out that this source might actually be the most likely source that LIGO 1 will see. Of course, there's all kinds of uncertainties, but let me tell you why, or give you an argument why. So if you want to look at the signal to noise that you're going to see from such a source, this is roughly goes like h, your gravitational wave amplitude, times the number of cycles, where this takes into account the fact that if you get more cycles, you can get a better signal to noise ratio. And you've already seen that from the quadrupole formula that this h goes something like m to the 5/3 over r, where now I've assumed equal mass holes. And you can also make the estimate that the number of cycles that you see, this is at a fixed frequency, is going to go something like the amount of time per cycle. So this is like f over f dot times the frequency. And you've already looked at what this f dot is in one of your homework assignments, and you find that f dot goes something like, again, it goes like mass to the 5/3. So if you combine all of these together, you find out that the signal to noise goes something like m to the 5/6 over r. And that means that if you could see up to a particular signal to noise, then the volume of space that you can look at, given that signal to noise threshold, so the volume probed is roughly like r cubed, and that's going to go roughly like m to the 5/2. So that tells you that the heavier of objects that you're looking at least in a certain range, the more likely you are to see them if they exist. And it so happens that if you have m, this is the total mass, is about 30 solar masses for the binary, then this is 400 times more volume than a neutron star binary, where neutron stars are about 1.4 solar masses. So what this means is that even though we know that there are probably more neutron stars out there than 15 solar mass black holes, if you do have some of these, you're going to be able to see them much farther away. And for this reason, it's thought that for LIGO 1, this might actually be the first thing that's seen. So the event rate that people estimate for this somewhere between, and again this is uncertain, 1 over 300 per year to about 1 per year for LIGO 1. For LIGO 2, for advanced LIGO, we're going to do much better. We're hoping to see a lot of these things. So for LIGO 2, the event rate is something like 0.1 to 1 per day, sorry, to 10 per day. And now again, here I'm talking about a total mass that's roughly 20 solar masses. So these are stellar mass black holes that I'm talking about here for LIGO 2. Now for LISA, you can also see binary black holes, except in this case, we're talking about masses that are somewhere like 10 to the 6th or 10 to the 7th solar masses. So these are supermassive black holes, say in the centers of galaxies. And the event rate for LISA is much smaller. It's something like 0.1 to 100. This is now per year. However, one thing that I should point out, the difference between what you might see from LIGO 2 and what you might see for LISA is that in this case, in the LIGO case, even though we're going to probably see a lot of them, we're going to see them at a pretty low signal to noise. They'll be detectable, but just barely, so signal to noise of a few. However, for LISA, even if we see one of them, people estimate that the signal to noise for these things could be 1,000 or higher, or 10 to the 5th or something like that, depending on how close they are. So if you see something like this with LISA, you're going to be able to measure the gravitational waves from such a black hole coalescence with extreme accuracy, and be able to test general relativity in the strong field regime if you look at merger waves, which I'll get to in a second. So such events are something that we expect to see. And let me talk about the stages of binary black hole coalescence. You've seen this, but just let me draw them. The first stage here is the in-spiral. And this is something that Alessandro talked about, that you usually look at gravitational waves from in-spirals using post-Newtonian methods. Once the two black holes are close enough after losing energy due to gravitational radiation, then you have the merger phase. And this is what I'm going to be concerned about. And finally, you have the ring down phase. And the ring down phase is basically once the merger has proceeded to the state where you have a single black hole, but that hole might be is not yet settled down into a static or a stationary Kerr metric. you still have ripples going on the surface of the black hole. You can see gravitational radiation from this ring down. So I'm going to talk about this here in a little bit more detail, this merger stage. So the first thing to note about the merger phase is that you have very rich physics going on, even compared to what's going on in the in-spiral and the ring down. So the fields are strong, so you have a lot of phenomena associated with strong field relativity that you have in the merger that you might not have in, say, in the in-spiral. And you get interesting effects having to do with angular momentum. So you get spin, 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 and spin, and spin orbit effects. So what I mean by that is that these black holes are going to have some spin angular momentum, and these spins are probably going to be in funny directions, and they're probably not going to be initially aligned with the orbital angular momentum of the system. And as these guys come together, there's going to be interactions both between the individual spins of the holes and between the spins of the holes and the orbital angular momentum. So you're going to see such things as these spins are going to want to align with each other, and they're going to want to anti-align with the orbital angular momentum. So the spins might be flipping around and doing all kinds of complicated stuff that we don't actually know the details of. We just, but you can guess qualitatively what's going to happen. Another thing that's related to this, maybe I'll call it spin hang-up, or centrifugal hang-up, and that is sometimes you might imagine that the two black holes would come together and merge very quickly. However, that might not happen depending on what these spins are and how they're aligned, what directions they're in compared to the orbital angular momentum. And that's basically because of all of this complicated dynamics that's going on, and the fact that once you form a final black hole, if you look at the final black hole, so Kerr black hole, you have to have the total angular momentum has to be less than m squared, less than or equal to m squared for a Kerr black hole. And depending on what the various angular momenta in the problem are, you might be going through various contortions in order to radiate away any extra angular momentum you have. So another thing to note about the merger waves is that these merger waves are going to be very strong. And they're going to be strong for two reasons. One reason is because you're in a more nonlinear regime of gravity where velocities are closer to the speed of light and masses are closer to the radii. And another reason is, at least for black holes that I'm talking about, for stellar mass black holes that are, once you get above 20 or 30 solar masses, then you start moving the merger waves into the middle of the LIGO frequency band, and the in-spiral waves are moving out of the LIGO frequency band. So let me show you a plot illustrating this. So this is taken from the review article by Kurt Cutler and Kip, which in turn is taken from an article by Anna Flanagan and Scott Hughes. And so what this shows, this is for initial LIGO. This shows the signal to noise that you'd expect for a binary at 1 gigaparsec, given the total mass of the binary. And one thing that you see is that for very small masses, if you follow up, say, for a total of 10 solar mass binary, the in-spiral waves are going to be much stronger than the merger or ring down waves. However, as you get past maybe 20 or 24 solar masses, you find that the merger waves are going to be much stronger than the in-spiral waves, at least. And again, there's two effects: one because the waves are stronger, and the other is because as you go past this part of the curve, the in-spiral waves are moving out of the frequency band where LIGO is sensitive. So let me also, if I can get this graph, I'm just going to flip this up very quickly because it's almost the same as the other one. This is a similar graph, and this is for advanced LIGO. And you see that qualitatively it's about the same, that as you get somewhere around 30-ish solar masses or more, the merger waves are going to dominate over everything. And once you get really high, then the ring down waves also are about the same strength as the merger waves. And just not to leave out Lisa, let me put up this graph. And this again is similar to the other two. One difference, other than it being busier, is that this axis, instead of just being the mass, the total mass, it's actually the total mass times 1 plus z, because with LISA you really have to worry about cosmological effects. And so so a vertical line on this is m times 1 plus z. So if you just want to see m, those are actually the dotted lines on this. So for instance, for 10 to the 6 solar masses, you see that at this point you can see where the in-spiral waves are, but the merger waves are going to be much stronger for 10 to the 6 solar masses, and you're going to be able to see essentially an order of magnitude farther. There we go. Okay, so we have rich physics and strong waves. So I probably don't have to say this, but we would like to compute what these waveforms are.
If they carry a spin.
They probably will carry spin. We have no idea. And so you probably know better than I do where what exact assumptions were used in making those graphs.
Yeah, so the Flanagan Hughes computations assumed large spins. Mm-hmm. And not well aligned. Of course, we don't know. You haven't told us yet what the real answer is.
Right.
And so they were guessing for large spins.
Right.
In their case, but in fact, we do know a lot thanks to the work of Alessandra and colleagues and others in the non-spinning case. And in that case, I think we expect that the merger waves may be weaker than, give us a smaller total signal noise rate than the total signal noise from the in-spiral waves.
Or it becomes important at very much higher masses.
Right.
Much more than 30 square miles.
Right. But we really don't know what the spins are. That's the.
We don't know the spins, but I think there are good astrophysical reasons to expect that the spins may be relatively large.
Right.
I mean, not.
Conservation of angular momentum in a supernova collapse and things like that.
But I think experience is that when astrophysicists think that they might know something, and nature often proves them wrong. When a relativity theorist like me speculates about these things, nature even more often proves them wrong.
Okay. So we'd like to be able to actually compute the waves from mergers and compute this process. And this would allow us to do several things. One is to aid detection. In the case of LIGO, and this is because detailed computations of these merger waves would allow us to build up templates that can be used for match filtering. We also can test strong field relativity. So these waves will probe a much stronger field regime of gravitation than say in-spiral waves do. And one other thing that we can do is actually distinguish black holes. So from in-spiral waves, say, really all that you care about is that you have some objects of whatever mass that are orbiting each other, and the calculation doesn't change very much, at least when they're far enough away, whether they're neutron stars, black holes, or what. However, once you have mergers, you have a signal that you can tell unambiguously whether it's a black hole or whether it's, well, not a black hole, or whether it's something that we haven't even thought of. So that's binary black hole coalescence. That's one of the main sources that we're interested in. Let me tell you briefly about another source. And this is neutron star tidal disruption. And so the idea here is that you have a neutron star and you have a black hole. Not this marker. In orbit. And as the two get closer due to gravitational radiation emission, eventually the neutron star is going to be ripped apart by the strong field of the black hole. So for LIGO 2, we might see the number that I found is somewhere between 15 through 50 of these per year. And the question is, how can you tell whether it's a neutron star black hole tidal disruption or whether it's some other binary coalescence? And the way that you can tell, you can tell by in-spiral cutoff. And what I mean by that is that you can look at the in-spiral waves for such a system, and they'll be going, and then at some point this neutron star is going to get ripped apart, and all of a sudden the waveform is going to change. And it'll probably mostly go away because depending on how much asymmetry is left, but if this neutron star ends up in, say, some sort of a disk about this black hole, it may not emit very much. Or you might see some sort of emission from the neutron star getting sucked in if it's sufficiently aspherical. But one thing that you should be able to see is the cutoff of this in-spiral, and this should be in the LIGO band, and should be visible. So one thing that you can do about this, or you can do with this, is you can measure neutron star equation of state. The reason you can measure this is because the exact point at which this in-spiral will cut off, and exactly what's going to happen, is going to depend on how big the neutron star is. And it's going to depend on the distribution of matter inside that neutron star. So for instance, right now, our best guesses for the size of a neutron star, so for a given mass, ask what the radius is, we only know that about up to a factor of 2. So, sorry. Known to however, if you measure these gravitational waves from such a system and figure out where this in-spiral cutoff is, then you'll be able to measure this radius. So say LIGO 2 should be able to measure this radius to something like 10% or 15%. And by knowing what the radius of a neutron star is for a given mass, that will tell you something about the equation of state of nuclear matter. So another reason that this is interesting is neutron star tidal disruption, is this is a possible gamma ray burst model. So once every day or so, we measure these large gamma ray bursts that are essentially not much is known about them in terms of details of how they're produced. We know various things like they're cosmological in origin and so on. And this is a possible mechanism for gamma ray bursts. And if we would see something like this in LIGO coincident with the gamma ray burst, this would tell us a lot.
How far away from LIGO is the event?
Good question, and I'm sure it's right here. I don't know off the top of my head. Maybe Kip knows off the top of his head.
LIGO 1 to about 45 megaparsecs, and LIGO 2 to
I'm getting 650.
3,000 times that, so about 650 megaparsecs. But to get the data at the high enough frequencies that you can measure the neutron star radii, you can see the end of the in-spiral. You can't do that to as big a distance because the end of the in-spiral is sitting up at higher frequencies than the minimum of the noise curve. So you cut back by maybe a factor of 3 in distance from those distances, or maybe 2 in order to do the nuclear physics. But to test whether, to do coincidences with gamma ray bursts, you you've got a coincidence, you can actually see about twice that far, but you don't need as large a signal-to-noise ratio on a coincidence. So LIGO 2 might be able to do coincidences with gamma ray bursts out to as far as a gigaparsec conceivably. If it's a neutron star black hole binary.
So another thing that I'd like to say about this problem is, of course, we'd like to be able to compute the gravitational radiation from this, and we'd like to be able to compute when, given a particular equation of state, when this neutron star is going to be disrupted. To do this, even though you can make reasonable guesses using Newtonian physics, and right now some people here, Michaela Vallisneri and Lee Lindblom, and are working on such a thing using Newtonian physics. To really get a firm answer, you're going to need to include relativity in this, because after all, both the neutron star and the black hole are relativistic objects. So there's also other sources that we might be interested in, and I'm just going to list a few of them. One of them we've probably talked about a lot already. Is neutron star merger. Now, the actual merger of the neutron star system, the waves from that are too high a frequency really for LIGO to see, but maybe some future instrument might be able to see this. But in any case, this system is interesting for some of the same reasons as the neutron star tidal disruption is, namely neutron star binaries are also candidates for gamma ray burst mechanisms. They also allow you to if you could measure such a thing, to be able to determine the equation of state, or the limits on the equation of state of nuclear matter. And then there's other more speculative things that you might want to look at, such as cosmic strings, or what I'll call brain excitations. And these have to do with topological defects in the early universe that might possibly produce gravitational waves, and that might be something that involves strong gravity. And these brain excitations are related to this idea that's been popular recently about our universe essentially being a membrane in a higher dimensional, say a 10-dimensional universe. And this would be some sorts of excitations of that brain. Of course, these things are very speculative. So, I'm now going to ask the question, what do these have in common? And by these, I mean all of these sources, binary black hole mergers, and all the way down to some of these speculative ones. So they have several things in common. One is that they have strong gravitational fields. So they're very non-Newtonian. Sort of going along with that is that they're fully nonlinear. So in computing any of these things to actually get all the relativity right, you can't use things like superposition. So for example, if I have a black hole here, and I know the metric is Schwarzschild, and I have another black hole here, that I know the metric is Schwarzschild. You can't just put them together and say that you have the sum of two Schwarzschild metrics. Things like that don't work. So you have to do something much more complicated. Another thing is that the usual approximations that you make are invalid. So what do I mean by the usual approximations? I mean such things like post-Newtonian, which works extremely well for some problems, will not work here because you assume things like V over C is less than 1, or M over R is much less than 1. And this is not true in the case of all these sources. Other types of approximations that people make are, say for a star, falling into a supermassive black hole. Here's another source that we've talked about. And in that case, you make an approximation if this is M1 and this is M2. You say M1 over M2 is very small. But in this case, at least for black hole binaries and neutron star black hole binaries, often you can't do this. You want to look at comparable masses, so you can't do this either. And sort of a general case that encompasses all of these is you cannot do this. You cannot say G mu nu is some G mu nu background plus H mu nu, where H mu nu is small. These are just special cases of that. But in this case, so you can't do that. So what else? The other thing is you don't know the metric ahead of time. So in something like relativistic hydrodynamics, or in E&M, what you usually do if you want to solve this relativistically is you solve equations, whatever equations that you're looking at, whether hydro equations, E&M equations, or MHD or whatever, you can solve them in curved spacetime. In curved spacetime. But here, you can't do that. Here you have to solve for spacetime. As you go along. So that's quite different. You don't start with saying, oh, I know the metric is this, and then continue. You actually have to solve for it. So the last thing that these have in common, which you probably have guessed by now, is there's no hope for an analytic solution. Because of everything that goes above. So the way to tackle these problems is to solve Einstein's equations on a computer. And this is numerical relativity. when I say on a computer, I usually don't mean the little laptop that you bring with you into class. Most of these computations require massively parallel computers where you have several hundred processors that you run your simulation for a month.
And you will do them on your laptop in the class in 5 years from now on.
Probably.
However, you will have discovered that you need the state-of-the-art computers of that era when you get to that era.
Oh, sure.
Right. So, if you want to solve Einstein's equation on a computer, the first thing that you have to do is actually write them down in such a way that they can be solved. So I'm going to talk now about ways to do that, and I'm going to talk about the usual way that people do this, although it's by far not the only method. And this is, well, this is 3+1 approach. And when I say 3+1, what I mean is the 3 stands for the 3 dimensions of space, and the 1 for the 1 dimension of time. So, in this approach, there's 2 types of problems. Or problems could be divided into 2 classes. The first, I'm going to call the initial data problem. And this is given some physical situation. At t equals 0, or at some constant time, what fields are allowed? And by fields, I mean the gravitational field, which is measured by the metric. The second type of problem is the evolution problem. And let me describe this by saying, given 1, the initial data problem, what happens later? For t greater than 0. And so, in order to solve these problems, there's 2 things that we need to know. One thing we need to know is how we break up Einstein's equations. So how do you break up Einstein's equations into space plus time? That's the first question. And the next thing that you need to know is which components of the metric you solve for. So let me just touch on the second question here first. You might naively assume that since the metric has 10 components, and since Einstein's equations have 10 equations, so 10 components of G mu nu, that you can say, oh, I have 10 equations and 10 unknowns and solve for all of them. This is wrong. You cannot do that. So, in general, can only solve for 6 components, and this is because the other 4 are taken up by gauge symmetry. I should say gauge freedom. Which, as you know, in general relativity, gauge freedom is really your freedom to choose 4 coordinates. And those 4 coordinates give you these 4 conditions, picking these 4 coordinates essentially determines 4 of these metric coefficients. And you can only solve for the other 6.
So Mihai wants to interrupt you to change tape.
Okay.
And while he's doing that, let me make sure everybody has course survey form.